Introduction to Exercise 8D on Line Graphs, page 436 of your textbook. Now this is going to be a nice short video because we're looking at one specific thing, which is the idea of line graphs. Now make sure you've got these notes in your notebook because it's very important that we go forward having this in mind. Some of you guys would have already seen line graphs before. If you haven't, we're going to go ahead and make one later, but first let's consider its properties. So a line graph is a connected set of points where we join them with straight line segments. You've seen them in real life before, whether it's temperature graphs or whatever it is. You've seen them because they're straight line segments connecting a set of points. If you haven't, you'll know exactly what I'm talking about in a moment. Now they use continuous numerical data, and it's very important that we refer back to that continuous numerical data. 2 lessons ago, we looked at the idea of numerical data, and remembering that numerical data is actually referring to data that comes in numbers. So for example, the weight of a certain animal or the number of pets, right? So numerical is referring to the number of something. And then from numerical, we've got discrete and we've got continuous. If you remember what discrete is, you remember that discrete means that it can only be whole specific numbers. So for example, whole numbers of, let's say, the number of pets you have, because once again you can't have 0.73 of a pet, that doesn't make sense, or the number of siblings, right? However, something like the height of each student in a class, that's continuous because we can have 1.65 centimeters or 1.48 centimeters, whatever it is. You can have continuous decimals in continuous numerical data, such as weight or height. And finally, we know that time is often on the horizontal axis in our line graphs. For this topic, I reckon we're going to jump right into an example to show you what it looks like from the outside. So in this example over here, and this example is found on page 438 of your textbook. In this example, temperature in a room is noted at hourly intervals, where we've got the time on the top row being shown as 9 a.m., 10 a.m., 11 a.m., etc. And we've got temperature on the bottom, which is going up what seems to be by 5 degrees, another 5 degrees, 3 degrees, and then goes down another few degrees. But we'll look at that in a moment. We have to present our results in a line graph. Now for this one, remember we're going to refer back to this third dot point where time is on the horizontal axis. So I'm going to go ahead and draw my axis over here with my horizontal one, and it looks somewhat similar to our Cartesian plane that we looked at a couple of topics ago. So we're going to go ahead and label our graphs. Remember that we need to label the graph by giving it a title. So I'm going to write room temperature over here, room temp, and then I'm going to go ahead and label our axes. So I've got time, and on the vertical axis I've got temperature. I'm going to go ahead and include the units as well as degrees. Okay, now I'm going to go ahead and label our time axis. So I've got 9 a.m. Let's go ahead and label that right here. I'm going to get rid of this space here. 9 a.m. there. And then up next I've got 10 a.m. and I'm just going ahead and filling in what we see in our top row here. Up next 11 a.m. 12 p.m. and then finally 1 p.m. Now we don't keep going, even though we know what happens after 1 p.m. We don't exactly know what the temperature is after 1 p.m. so we leave it at that. I'm also going to label my temperature itself. Now I know that the highest number is 23. So I'm not going to go past 23 by much. I could go past it, but I'm not going to go ahead and go to count to 153 because that's going to be a waste of time. So let's say that's 5. Let's use a different color. There we go. 5, 10, 15, 20, and finally 25. I don't need to go any further than that. Okay? Too easy. Now all we have to do is represent the results in a line graph by actually including the data. Now in the first column, I've got 9 a.m. and it was 10 degrees. So I go to 9 a.m. and I go up to 10 degrees and I put a dot there. That's all I do. Up next, we have 10 a.m., which was 15 degrees. So I'm going to go 10 a.m. up to 15 degrees, which gives me a point right about there. So it should line up with my 10 a.m. and also my 15 degrees there. Up next we have the point 11 a.m., which is 20 degrees. So that goes up to here. 12 p.m., which is 23 degrees, which is, let's say, about there. And finally, for 1 p.m., we've got 18, which is approximately there. Now, your graphs don't have to be perfect, but it's a really good idea to be drawing them as neat as possible, because you're going to be needing to actually identify bits of information based on your graph itself. Now, you can see in my graph, even though it may look like it, not all the lines are going to be perfectly straight and continuing in the same direction, as you can see by this last line here as well. Okay, so we've represented our results in a line graph. Now we need to use the graph to estimate the room temperature at 12:30 p.m. Now I know 12:30 is between this time of 12 and this time of 1 p.m. So I know it's exactly half. I'm going to go ahead and grab my ruler and try to draw exactly half. Let's say about there. I'm going to do a dotted line up to the top so I can see. I know it is approximately at that time. I'm going to go ahead and grab my ruler, turn it the other way, and see exactly, or try to see exactly, what temperature it'll bring me to. Now, by the looks of it, it looks to be about 21 degrees. So I'm going to write 20 degrees there. If you write 21 degrees and it says estimate based on your graph, then you won't lose marks if you write 21 or 19 degrees or 22. But if we're going to 23, 24, 25, that's pushing it a little bit. Hopefully that makes sense. We're going to be looking at something else called a travel graph, which is just a specific type of line graph. Basically, it's just a line graph in application. Now, if you need to go back and watch that section there to copy down the notes, please do so by pausing the video and copying down those notes. Great. Let's continue on. So, a travel graph shows us how far someone goes in terms of distance over a certain period of time in terms of time. So, for example, we've got here someone cycling over 5 hours. So we can see over here on the bottom side, the horizontal axis gives me over 5 hours. And over here, we've got the distance someone travels in kilometers over those 5 hours. Now you notice that for our graph, the person's distance doesn't go down, because we don't go down in distance, can we? We don't reverse. That's not how it works. So our distance goes up, but it might go up at different speeds or at different times. So all we have to do is look at this graph and be able to answer the questions based on this graph here. So how far did the cyclist travel in total? Well, what I can do is I can look at the very beginning, which is right here. I can say, okay, distance is 0. And then look at after 5 hours, what's the distance? Well, I know that the distance is, by grabbing a ruler and measuring across, 30 kilometers. So I know that in total, this cyclist traveled 30 kilometers. That's it. How far did the cyclist travel in the first hour? Now here's where we have to follow the line graph. I can see here that in the first hour, it goes up, because remember, 1, this is time in hours. It goes to 15. Now I've drawn that a bit crooked. There we go. It goes to about 15. So I can say in the first hour, this cyclist travels 15 kilometers. Remember that we need to actually make sure that we're following what the question's asking, because in question C, it says, what is happening in the second hour? Well, in the second hour, I know that this is the first hour, and then in the second hour, it is this period of time between this point and that point there. So in that period where we've got that second hour, I know that that person or that cyclist isn't increasing in distance, nor is he decreasing in distance. So what we say is that they are at rest. Now if you write not moving, that's also a valid response, but in mathematical terms and also scientific terms, we say at rest. For question D, when the cyclist, or the question's asking, when is the cyclist traveling at the fastest? Now you'll notice that for this graph here, in the first hour, they've gone from 0 to 15 kilometers. So they've traveled 15 kilometers in that single hour. If I look at it from this side here, over a period of 2 to 5, which is 3 hours, they've traveled 15 to 30 kilometers, which gives me 15 kilometers. So even though it is the same distance, it only took them 1 hour in the first hour versus 3 hours in the second bit. So I'm going to say, well, the fastest they're traveling, or the time that they're traveling the fastest, is in the first hour. And then finally, for this question here, it says, in the 5th hour, how far does a cyclist travel? So in the 5th hour, so that would be the 1st hour, 2nd hour, 3rd hour, 4th hour, and 5th hour would be between 4 to 5. So we're going to focus on those points there. I'm actually going to use a ruler just to make sure we've got an accurate answer. There we go, line it up there, and I'm going to go ahead and draw between those points there. So I can see that that point right there is the distance after 4 hours, which happens to be, and you'll remember our Cartesian coordinates, 4, 25. 4 hours, 25 kilometers. And this final point, you'll know, is 5 hours and 30 kilometers. Now remember, this is my x-axis, this is my y-axis, and it's always x comes before y. So we have those 2 points there. Now I'm thinking to myself, well, I've got those 2 points. How far does the cyclist travel? I know that they went from 25 kilometers to 30 kilometers, which gives me a distance of, well, I can write that out actually. 30 take away 5, so we end up with 5 kilometers. And that would be our final answer for part E. Hopefully that makes sense. Please let me know if you have any questions. Otherwise, best of luck. Please get started on questions for exercise 8D.